Hello everybody. In this video we are going to be looking at the solutions to the college prep sound homework problems 6 through 10. We'll start with problem 6. It says ultrasound with a frequency of 4.25 megahertz can be used to produce images of the human body. If the speed of sound in the body is the same as in salt water, which is 1.50 kilometers per second, what is the length of a 4.25 megahertz pressure wave in the body? Let's take a look at what we are given here. We are given the frequency of 4.25 megahertz. And again, I know that's frequency. A tells me that's frequency right here. And I also have the unit of hertz. So that tells me that we have a frequency. So megahertz, I do need to convert that to hertz. So 4.25 megahertz, the prefix mega means 10 to the 6th or 1 million. So that's going to be 4.25 times 10 to the 6th hertz. The speed of the sound wave is 1.50 kilometers per second. Again, do need to convert that to meters per second. So to do that, I know that I'm going to end up with 1.50 times 10 to the 3rd meters per second. And we are looking for the wavelength, which is represented by our lambda. So I have the frequency, I have the velocity, I am looking for the wavelength. In this problem, I need to use my wave speed formula. Velocity equals frequency times the wavelength. Rearrange my formula to solve for wavelength. I have the wavelength is equal to the velocity divided by the frequency. So I take my velocity of 1.50 times 10 to the 3rd meters per second, divide that by my frequency of 4.25 times 10 to the 6th hertz, and I'm going to have a wavelength of 3.53 times 10 to the minus 4th meters, or 0.353 millimeters. Problem 7. A ship surveying the ocean bottom sends sonar waves straight down into the seawater from the surface, as shown in the figure. The first reflection, which is off the mud at the bottom of the seafloor, is received 1.74 seconds after it was sent. The second reflection from the bedrock beneath the mud returns after 2.36 seconds. The speed of sound in seawater is 1,533 meters per second, and the speed of sound in mud is 1,875 meters per second. The first thing they want to know is how deep is the water. So if we have to find out how deep the water is, we need to know the time that it took for the sound wave to reflect off the mud at the bottom of the ocean and back up to the ship, which was 1.74 seconds. Now that's the total time it took for the sound wave to go from the boat. Oops, let's see if I can do this with highlighter here. The boat down to the seafloor and then back up to the boat to make a round trip. To find the distance between the boat and the seafloor, I need half of that time. So I need to take my total time the sound wave took to travel in the water and divide that by half. So I take 1.74 seconds, divide that by 1/2, and I will have a time for the one-way trip of 0.87 seconds. Now I'm also given the time it takes for the sound wave to travel in the mud. That'll be useful for the second part of the problem, but I don't need that here. I am given the velocity of the sound wave in seawater, which is 1,533 meters per second. I'm also given the velocity of the sound wave in the mud, which again, I don't need just yet, so I can ignore that. And the two things I want to find, or the thing I want to find first, is going to be the depth of the water. So in order to find the depth of the water, I need to know just how fast the sound wave is traveling in the water, which is 1,533 meters per second, and how long does it take to travel that distance, which was 0.87 seconds. When I multiply the two of those together, I am going to have a depth of the ocean of 1,300 meters. Part B asks, how thick is the mud? Now, for the first part, what we were able to do was just take the total time that the first sound wave traveled in the water and divide that by 2, and that gave us the time for one-way trip for that sound wave. That doesn't work with the second sound wave because it's traveling through two different mediums. That second sound wave starts off traveling in the water. I'm going to try this again, traveling in the water. Then it hits the mud and it starts traveling in the mud, so it's going to be moving at a different speed. It's moving at 1,533 meters per second in the water, and then once it reaches the mud, it's traveling at 1,875 meters per second. Then once it gets that boundary again between the mud and the seawater, it goes back to traveling at 1,533 meters per second. So that sound wave is traveling at two different speeds. What we do know, though, is that the difference of the time that it takes the first sound wave to travel, which was 2.36 seconds, or the second sound wave, 2.36 seconds, and the time it takes for that first sound wave to travel, which was 1.74 seconds, that difference is the total round trip that it took in the mud here. So the total round trip time for the mud is going to be 2.36 seconds minus 1.74 seconds, which gives me 0.62 seconds. That's the total time the sound wave was traveling in the mud, a round trip down and then back up. To find the one-way time that the sound wave was traveling in the mud, I have to take that 0.62 seconds, divide it by 2, which is going to give me a one-way time of 0.31 seconds. So now I know how much time the sound wave was traveling in the mud at 0.31 seconds. I know how fast it's traveling in the mud, 1,875 meters per second. So now I can calculate the distance by multiplying the velocity times the time. And when I do that, I am going to have a depth of the mud of 580 meters. Problem number 8. A fire truck is moving at 35 meters per second, and a car in front of the truck is moving in the same direction at 15 meters per second. If a 327 hertz siren blares from the truck, what frequency is heard by the driver of the car? So this is going to be a Doppler effect problem because we have a sound wave being emitted by a source that is moving relative to an observer. So let's see what we are given in this problem. We know that the velocity of the source of the sound wave, which is the fire truck, specifically it's the siren on the fire truck, but a siren is moving with the fire truck. So the velocity of my source of the sound wave is going to be 35 meters per second. And it's going to be a positive 35 meters per second because the truck is moving in the same direction as the car. It's moving toward the car because we have the car in the front and the truck in the back. The observer of the siren or the sound wave is going to be the driver of the car, and the car is moving at 15 meters per second, but the velocity of the observer is going to be negative 15 meters per second. And remember, we define, and this is going to be important, we define the sign of the velocity according to the relative motion between the observer and the source. If the source or the observer is moving toward the other, so if the source is moving toward the observer or the observer is moving toward the source, their velocity is going to be positive. If the source and or the observer is moving away from the other, then their velocity is going to be negative. So if we take a look and see what happens in this problem, here is my fire truck. I don't know what a fire truck looks like. I'll call it this. This is my fire truck. And here is my car. And here's my observer. Okay. The fire truck is moving in this direction at 35 meters per second. The truck is moving toward the car. The car is moving in the same direction at 15 meters per second, but the car is moving away from the truck. So even though they're going in the same direction, the fire truck has a positive velocity and the car has a negative velocity because the fire truck is moving toward the car, but the car is moving away from the fire truck because the car is in front of the fire truck. Now, the frequency of the sound wave that is emitted by the fire truck is 327 hertz. and the frequency that is observed by the driver of the car is what we are looking for, trying to find. So we are going to use our Doppler equation for this problem. And we know that the frequency of the observer is equal to the frequency of the source, which was 327 hertz, plus the velocity of the sound wave. So this V right here and this one here are both the velocity of the sound wave. How fast is the sound wave traveling? So because we don't specify a temperature, we are going to assume that the temperature is 20 degrees Celsius. Whenever I don't specify a temperature, assume that it's 20 degrees Celsius because that's what we refer to as room temperature. And the speed of a sound wave at room temperature, or 20 degrees Celsius, is going to be 343 meters per second. That's something you're just going to have to know. Now we have to put in the velocity of the observer, which is minus 15 meters per second, and the velocity of the source, which is positive 35 meters per second. So remember, this negative sign is embedded within the equation. So this would read 343 meters per second minus a positive 35 meters per second. And when we do that math out, we are going to have an observed frequency of 350 hertz. So just to recap, the fire truck, the siren on the fire truck emits a sound wave at 327 hertz, but because of the motion between the observer and the fire truck, the observer in the car is going to hear a sound wave at 350 hertz. The tricky thing with these equations, and if I just kind of make some erasures here, the tricky thing with these equations is that we have three velocities that we have to keep track of. We have the velocity of the sound wave, which again, unless I specify something different, is always going to be 343 meters per second, which is my room temperature. I have the velocity of the observer, and I have the velocity of the source of the sound wave. So that's one thing you have to be very careful of in these problems and to try to keep track of. Problem 9. A train moving toward a sound detector at 31.0 meters per second blows a 305 hertz whistle. What frequency is detected on each of the following? So first of all, let's take a look and see what we're given. We know that we have the source of the sound wave, which is the train moving at 31 meters per second. So that's the velocity of my source. The frequency emitted by that source is 305 hertz. And again, I don't specify a temperature, so I'm going to assume room temperature of 20 degrees Celsius. And at 20 degrees Celsius, I know that the velocity of the sound wave is going to be 343 meters per second. First thing I want us to find is the detected frequency on a stationary train. So we have one train moving at 31 meters per second approaching another train that is stationary or not moving. So in that case, my observer, or the velocity of my observer, is going to be 0 because it is stationary. And we are looking for the frequency that is detected by the observer. Once again, we're going to use the Doppler formula, and I know that the frequency of the source is 305 hertz. The frequency of the sound wave, because we are assuming room temperature of 20 degrees Celsius, is 343 meters per second. The velocity of my observer is 0, and the velocity of the source is 31 meters per second. Because the source is moving toward the observer, it's going to be a positive 31 meters per second. So we have 343 meters per second minus a positive 31 meters per second. And when we do that math out, we will have an observed frequency of 335 hertz. Part B of problem 9 asks, what is the observed frequency on a train moving toward the first train at 21 meters per second? So the two trains in this scenario are both moving toward one another. Hopefully they're on different tracks. We can assume that. But because both trains are moving toward each other, the velocity of the observer is going to be 21 meters per second, and it's going to be positive 21 meters per second because it is moving toward the observer. And when I put that into my Doppler formula, I have 305 hertz is my frequency of the source still. Sound wave is still traveling at 343 meters per second. My source is still moving at positive 31 meters per second, and my observer is now moving at positive 21 meters per second. And when I do that math out, I'm going to have 350 something hertz. I can't tell because when I do the videos, my face is down in the corner and I am actually blocking the answer right now. So I can see it's 350 something hertz, but I can't see the exact answer. But after I'm done recording the video, I'm going to lift myself up to right about there and you'll be able to see the answer, but I can't see it right now. So you can see what it is. I'm not going to say it. You guys can read. Problem 10. The train in the previous problem is moving away from the detector. And what frequency is now detected on each of the following? So a lot of my information has stayed the same from the previous problem. The velocity of my source is still 31 meters per second, but now it's negative 31 meters per second because it is moving away from the detector or the observer of the sound wave. So it is going to be a negative velocity, so negative 31 meters per second. The frequency of the source is still 305 hertz, and we are still assuming room temperature of 20 degrees Celsius will give me a velocity of the sound wave of 343 meters per second. So the first thing that they want us to do is find the observed frequency on a stationary train. So we are again looking for the observed frequency, and we know that the velocity of the observer is going to be 0. So to find the frequency of the observer, once again, we are going to use our Doppler formula. A lot of this is going to stay the same from the previous problem. The frequency of the source is still 305 hertz. The sound wave is still traveling at 343 meters per second. The velocity of my source is now negative 31 meters per second. So notice I have 343 meters per second minus a negative 31 meters per second. So that really just means that I'm going to add those two values together. And the velocity of my observer is 0 because they are stationary. And when I do all of that math together, I am going to have an observed frequency of 280 hertz. And finally, part B of problem 10 asks us to find the observed frequency on a train or observer on a train moving away from the first train at a speed of 21 meters per second. So now the velocity of my observer is going to be negative 21 meters per second. And it is a negative because the observer is moving away from the source, which is the first train. Once again, I'm going to plug all of this into the Doppler equation. A lot of this is still staying the same. My frequency of the source is still 305 hertz. The velocity of the sound wave is still 343 meters per second. My velocity of the source is still going to be negative 31 meters per second. And the velocity of my observer is negative 21 meters per second. And when I plug all of those into my Doppler formula and I do out the math, I will get an observed frequency of 263 hertz.